Hello everybody, this is Dr. C. Pre-lecture today is going to be pretty darn short. We're going to focus on the second law of thermodynamics. So let's just get started. So what does the second law of thermodynamics tell us? So reading the first bullet point here, let me get a pen real quick. The entropy of the universe increases in a spontaneous process and remains unchanged in an equilibrium process. Don't worry too much about equilibrium for now. We'll come back to that toward the end of the chapter. But really what we use the second law of thermodynamics is one method to predict spontaneity. Okay. And you may or may not remember, but at the start of the semester I kind of hinted that this is the main goal of this chapter. How do we predict whether a reaction is going to happen, whether it's spontaneous? This is one method we're going to use. We're going to look at a second method as well, but this is the first one, the second law of thermo. So spontaneous, the entropy change of the universe, which is composed of the system and the surroundings, needs to increase, positive, greater than zero. So that is a spontaneous process. We can qualify that a little bit more by saying it's spontaneous in the forward direction. Now, that might seem a little redundant, but when we say spontaneous, if we say a reaction is spontaneous, we mean reactants going to products in the forward direction. Thereby, it would not be spontaneous in the reverse direction, products going to reactants. Okay, so spontaneous in the forward direction. Don't worry about equilibrium for now. We'll come back to this zero thing here. If we ended up calculating a delta S of the universe that is negative, less than zero, okay, that would not be spontaneous. In the forward direction. Okay, so a decrease in the entropy of the universe would not be spontaneous in the forward direction, but that reaction would be spontaneous. In which direction? Reverse. So products going back to reactants. So we turn the reaction around and it would be spontaneous. Okay? So, second law of thermo, entropy of the universe increases in a spontaneous process. And so we're going to actually look at how we calculate that. Well, look at this equation here. To get the entropy change of the universe, we need the entropy change of the system and the surroundings. Let's see how we do that. Well, before we go to delta S of the surroundings, let me just say, we know how to calculate delta S of the system, right? Right? Can you hear me now? We're going to use system and reaction interchangeably. Okay? So for us, our system is our reaction. And we can calculate that summing together the standard entropy values of the products and subtract off the standard entropy values of the reactants. All right? So one part of calculating the entropy change of the universe, we already know how to do. Okay? From the standard entropy values of products minus reactants. The part we don't know is this one, delta S of the surroundings. Okay? And what we're going to find is that the entropy change of the surroundings will depend on the heat flow of the system. All right? So I think, for example, it's easiest to first look at an exothermic reaction. So our system is releasing heat in this case. Everybody agree with that? So our system releases heat. Now our surroundings out here are going to be impacted by the thermal energy. Let's say our surroundings are just the air molecules that are surrounding that reaction. When those air molecules, the nitrogen and oxygen molecules, absorb thermal energy that comes out of the system, they're going to start moving faster. They're going to collide with more energy. They're going to have a greater entropy. Okay? So the heat flow from the system will impact the entropy of the surroundings. So this is what this is saying up here. The entropy of the surroundings is proportional to the entropy change of the system. The entropy change of the system. Sorry. the enthalpy change of the system, delta H. Sorry about that. So the entropy change of the surroundings is proportional to the heat flow from the system. Now, why the negative sign? Why the negative sign? And that's because if it's exothermic, and we're focusing on exo, it's going to be opposite for endo. But for exo, delta H is negative. All right? So now that heat flowing out of the system is going to increase the entropy of the surroundings, which will have a positive sign, an increase in entropy. So if we have a negative delta H, exo, we're going to have to change the sign by putting another negative sign up here in front of the equation to make sure we get a positive entropy change. Okay? Now, one more thing to consider. So the entropy change of the surroundings certainly proportional to the negative enthalpy change, delta H, of the system. We know that. But it also depends on the temperature. So let's just read through this first bullet. If the temperature of the surroundings are high, the molecules are already quite energetic. Okay? So the higher the temperature, the higher the kinetic energy of the surroundings. Right? So even if it is exothermic, if the surrounding molecules are already quite energetic, that heat flow coming out of the system is not going to have as much of an impact. It will have relatively little impact on the molecular motion. So if the molecular motion is already really high, adding more thermal energy to that isn't going to have as big an impact. So it's also proportional to 1 over the temperature. So if the surroundings are already at a high temperature, then the entropy change is going to be smaller. If the surroundings are at a lower temperature, the entropy change will be larger. Okay, so depends on enthalpy, heat flow into and out of the system, depends on the temperature of the surroundings. We put those two things together, and we end up with this equation. So we can calculate the entropy change of the surroundings using the enthalpy change of the system, the heat flow. Heat flowing into or out of the system will affect the surroundings, and it's also proportional to 1 over the temperature. And again, it's maybe a little harder to understand, but again, it's about the energetics of the surroundings. If they're already highly energetic, heat flowing out of the system, say, wouldn't have as big of an impact. If their molecules of the surroundings are moving very slowly, then heat flow, say, out of the system would have a much bigger impact. Okay, proportional to 1 over the temperature. So there we go. Do you know how to calculate delta H of the system or delta H of the reaction? Sure you do, right? We sum together the delta H of formation values of the products, and we subtract off the delta H of formation values of the reactants. All right, so to sum it up and wrap up this pre-lecture, our main goal here is to predict spontaneity, and I can spell. And we're going to do that by calculating the entropy change of the universe. This is from the second law of thermodynamics, that the entropy of the universe will increase, be greater than 0 for a spontaneous process. And we're going to calculate that entropy change of the universe using the entropy change of our system and the entropy change of the surroundings. And we talked about how to calculate both these parts. The surroundings is right up here. The system is, again, just to remind you, is we're going to sum together the entropy changes, or the standard entropy, of the products, and subtract off the sum of the standard entropies of the reactants. All there is to it. I think I was under 10 minutes. Could be a record, maybe not. All right. Hope this is clear enough. I'm not going to solve a problem. You're going to solve a problem calculating delta H in the pre-lecture, or the pre-lecture quiz, delta S, or delta H of the system in the pre-lecture quiz, delta S of the system in the pre-lecture quiz, and then you're going to put all of that together to get delta S of the universe in the third problem. So there's 3 calculations you need to do for the pre-lecture quiz. All right, there we go. See you in class soon. Take care.